Earlier, when introducing DFT, I alluded to the fact that we could use the coefficients we find from the discrete Fourier transform to make an analysis about our original time series using spectral analysis or seeing the power spectral density of the signal. So briefly, what the PSD is going to show us is the strength of each frequency component to that original signal. And we're going to show that here by calculating for every frequency what its power contribution is. So we're going to use the power as taking for any frequency, we're going to take that A coefficient squared plus its B coefficient squared and take the square root of that. So this step is going to be done after we do the DFT and capture our coefficients. Let's take those coefficients and compute the power. So the larger the A value is and or the B value is at any frequency, at the nth frequency, the larger the power contribution is at that frequency. So we do our DFT, we're going to have all of our A and B values for all of our terms. For each term, we're going to calculate the power, and the power is actually what we're going to be analyzing with the PSD. So typically, we want to be plotting this in decibels when we make the visualization of our power spectral density that we'll see in the forthcoming example, what it actually looks like. Now, using the DFT techniques that we just looked at before and then calculating the power this way, we're getting a fairly primitive power spectral density. For time series that are long, where we have lots and lots of samples over lots and lots of periods, that there are going to be better ways in order to smooth or filter our data. So I'm not going to be talking about more advanced methods for doing our PSD, which is things like windowing, where we're taking small subsamples of our time series and then starting to basically average them together. And this is going to be good if we have noisy data that on average the noise, the high noise and the low noise are going to average each other out. That's what windowing is going to take care of. And there's other things too in more advanced methods for calculating the power or for conducting a power spectral density. So one really good tool in MATLAB that's built in is the pwelch, which is going to be able to do a power spectral density analysis for us, and it has built into it a lot of these really nice features like windowing. So I'm not going to address that now, but it is a good tool to look into in MATLAB. And once again, for analyzing the power or the contribution of each frequency to the original signal, I want to just stress again that we are looking at these stationary signals. So when we make this power spectral density, it is taking an average more or less across time, and that's what the DFT does when we're calculating those A and B coefficients, because we're adding up all of the time signals and giving them equal weight. If we have a signal that's not stationary, we can do the wavelet analysis, which is going to be kind of like adding a dimension to our power spectral density, because now we're taking averages over smaller amounts of time, but then we are going to kind of piece them together so we can see how the frequency contributions are going to evolve over time. So that's the very basics of what we're doing with the spectral analysis. The forthcoming example is going to really illustrate what does this all look like and what does the PSD, again, tell us about our original signal.